Thank you. Wish you all the best again once more for your long life and productive life. So let me also thank, on behalf of the organizers, the organizer. Thank you. I'm going to talk today about the regularity of the density of states. I'll tell you what it is. My name is Krishna. I work in a university called Ashoka University, which is a private university in north of India. It may not be well known. It's a liberal arts and sciences university. So what I'm going to talk about today is a joint work with Dhriti Dolai, who is here, and Anish Malik. Both of them are my former students. So the question I'm going to look at is the following, if I'm allowed by the slides. I look at two classes of operators. On L2 of RD, I look at the Laplacian plus a random operator of multiplication by the functions un multiplied by omega n, which are random variables, summed up over n. So that's an operator of multiplication by this function, which is a random function. That's on L2 of RD. And on L2 of ZD, I look at some bounded operator and some diagonal operator of this type, where the rank of Pn could be any finite number. The supremum of the ranks should be finite. So that is the condition that I have. So in these models, the numbers omega n's are independent random variables. They have distributions which are absolutely continuous with the densities given by the functions rho n. And in general, these operators, the Laplacian could be replaced by something more general, and H0 is bounded, as I said, bounded self-adjoint. So given this, given any self-adjoint operator A, you have, by the spectral theorem, a projection valued spectral measure. So I will look at the projection valued spectral measure. Then for the operators that I mentioned earlier, if I take h omega on L2 of RD, look at the spectral measure of the interval minus infinity to E, that operator is a projection which may not be trace class, but if you multiply this by the U0, then this becomes trace class for every fixed E, and you take its trace, then that trace is a distribution function of a measure, a numerical measure. That distribution function is random. So you take the average, and if you take the average, you get some distribution function, which I call NC of E. And similarly, for the discrete case on L2 of ZD, do the same thing. Take this self-adjoint h omega of this interval and consider the trace class. P0 is finite rank, so that is automatically trace class. So look at the trace and take the average, and that's a measure. That is a distribution function of a measure. So these are the quantities I am going to look at as E varies. So the question I am going to ask is, how regular are these two functions? By now it is well established that both these functions are differentiable almost everywhere. And for the Anderson model, that is our model on L2 of ZD, this function is also smooth as long as rho n's are smooth.
Did you say what the U-naught function is?
Did I say?
Did you say what the U-naught function is? The previous class.
u0, that is the function here, some function that I take, right. These are some bump functions which form a partition of unity. I will tell you the condition later, but for now we can take the sum of n in ZD of u of un of x should be the constant function. So, I will require this condition later. Okay. They are functions which are bounded by, so if you want more specifically, UNs are smaller than or equal to 1, non-negative, and form a partition of unity. Okay. So, these functions were known to be absolutely continuous, have a derivative almost everywhere. And in the case of L2 of ZD, this function, you also know that it is smooth, it was shown earlier, and its smoothness is based on that of rho n. Such theorems were proved in the mid 1980s. It started by a paper by Barry Simon and Taylor, followed by papers of Abel Klein and co-workers. So, all of them around the same time. Prior to that, there were some theorems on analyticity of these objects in a regime called a large disorder, but all those results were only for L2 of ZD model. For L2 of RD, not even the continuity of the derivative of this NC is known, was known. Okay? It's that sort of a problem. So, in the case of NC, not even the continuity of the derivative was known in any dimension, and this problem had been open for more than 30 years. So, we will look at this question, and before I answer this question, let me give you a feeling for why this question seems to be difficult. So, let us take a 2 cross 2 matrix A, Hermitian matrix, something, add a diagonal to it x y 0 0, where x and y are independent variables. So, I get a 2 cross 2 matrix that depends on x y. Now, look at the eigenvalues of this. It will have two eigenvalues, lambda 1 of x y, lambda 2 of x y. Let me order them like this. Typically, they are not going to coincide. Then you look at the distribution function of this. So, lambda 1 is here, lambda 2 is here. So, look at the function that is 0 and jumps by half when you hit lambda 1 constant, and again jumps by half when you hit this. So, look at this function n of e. As e varies here, n of e is this function. Of course, because lambda 1 and lambda 2 depend on x y, this also depends on x y. So, what we are asking is, look at the integral of n of x y at e, rho of x, rho of y, dx, dy. Call this function n of e. So, we are asking the question that if these two functions rho are smooth, then this function is smooth. In other words, if rho has 10 derivatives, does n have 10 derivatives? So, if you look at the question like this, it looks like it's an impossible question to answer, right? It's not even obvious why this should be true. So, the questions that we are asking here are of that nature. Instead of having a 2 cross 2 matrix, we now have infinite dimensional objects. In the L2 of ZD case, we do have matrices, and L2 of RD case we have operators. So that is a kind of a question. Now the point is to look at these objects. Somebody taught me that Grothendieck's philosophy is that you put everything in the correct language and all theorems follow the statements. So something similar happens here, at least a part of the problem. You put it in the correct language. So I assume here that omega n's are independent random variables distributed according to rho n, and the UNs are translates of one function with compact support, so that they form a partition of unity. And there are some statements about stationarity and so on. So let me. So there are these assumptions, but let me give. I'll come back to this. I think. Yeah. The essential point here is, for problems of this nature for the matrix, what you have to notice is that so if I take any bounded operator A on any separable Hilbert space and take positive operators Tn with the property that they add up to, that they form a partition of unity, that is sum of Tn's is identity, and multiply each Tn by omega random variables omega n and add it up, finitely many of those, and look at the operator A omega. Then when omega n's are independent and you look at a function g, which is a complex valued function of this operator A omega minus e times identity, then this quantity actually turns out to be a convolution of two functions. So omega n's are n in number. So the vector formed by omega n's is a point in Rn. I don't know what. So that's a point in Rn, and no, I think forget the slides. I'll write it. No. I think the slides are messed up. So the idea is this. I have the A omega, which is some A plus sum of omega n Tn. So if I take A omega minus e times identity, I can write this as A plus sum of omega n minus e times Tn, n equal to 1 to n. Okay? So because of this, what happens is that if I take any function of A omega minus e, this is a function in Rn, some function of minus e minus e times a vector omega 1 times minus omega. This is the object. So if I take the average with respect to product of rho of n of omega n d omega n, then that average is nothing but some function phi of omega d omega. Therefore, this is nothing but it's a convolution. So this is of the form some function f star phi along the vector e times 1. That is this quantity. So whenever we take a complex valued function of A omega minus e where these Tn's satisfy sum of Tn is the identity, it is a partition of unity, then this average is nothing but a convolution. So, once it is a convolution, we know that convolutions are smoothing. So, if you write that integral in the correct format as a convolution, it is obvious that as a function of E, this function is smoothing, because once you have a smooth function in Rn, you convolve it with a bounded measurable function, then the result also becomes smooth in any direction. So, in particular in the direction of the vector 1, the directional derivative exists as many times as you have the sum of the derivatives of these functions. Okay? So, it is this fact that is at the heart of saying that matrices like this, when you take averages, the resulting functions are smooth, provided the functions are smooth.
I have one question about the statement. You had one row, but they are all different, right?
Yeah.
In the statement of the theorem.
I can take rho 1, rho 2, it does not matter. If each of these has m derivatives, then the product has m derivatives, and therefore, you are convolving with a function which has m derivatives as a function on Rn, and therefore, the convolution is smooth, has so many derivatives. So, it is the statement as simple as that. Okay? So, once we have that statement, what we do what we do is these functions, forget these numbers, they are just numbers, we can omit them. These averages we can write as follows. So, we can write these averages as average of trace of say u0 E of h omega minus E, this operator E times identity acting on 0 to minus infinity to 0. So, this becomes a fixed bounded measurable function, and you are taking the average. Okay? So, it becomes a convolution. The only problem is in these cases, in the case that we have here on L2 of Rd, this operator has infinitely many variables. So, convolution on infinitely many variables is a problem. Whereas, if somehow we could cut down this operator to finite number of random variables, as we do here, so what we do is we take h omega and compress it to a box lambda, which is same as saying that I take in Rd, take a box lambda with the property that lambda intersects Zd has finitely many points. Okay? Then the number of random variables you have there are only finitely many. So, because they have finitely many, these functions are convolutions of finitely many rho n's. So, it is a convolution on Rn, and therefore, these functions when lambda is a finite box are smooth both in Zd and Rd. But the difficulty is that once you take a derivative in convolution, you have to transfer the derivative to this function here, All right. So if I have integral sum function f of x minus y, product of n going from 1 to n, rho n of yn, where y is a vector and x is a vector dyn. When I want to take a derivative here and I transfer it to y, I have to take derivatives in n variables. When I take derivatives in n variables, there is a sum of terms. So when the number of variables increases, the sum increases, and when it goes to infinity, it's difficult to control the sum. So you have to control the sum somehow. That is the difficulty. And that is why this problem was open. Nobody could control the sum. Right? So what we do is take a finite box, restrict the operator h and little h to the finite box lambda, look at the density of, look at these distribution functions for the corresponding operators. They are smooth, and then we have to let the box go to infinity. Okay? So for doing this, what we do is use an estimate in a part of the spectrum called the exponential localization. So it is, I'll restrict myself to L2 of ZD case, L2 of RD is similar. So when you take the operator h omega on L2 of ZD and take a point in the upper half plane, this resolvent is a bounded operator, and multiply by the spectral projection, by the projections Pn and Pm that we considered as part of the operator. Remember that h omega was sum h0 plus sum of omega n Pn. So it is these Pn's that we are looking at. So when you multiply this and take the norm to the power s and take the average, it was shown that in some part of the spectrum, the norm decays exponentially fast as the distance between the points. This region of the spectrum is called exponentially localized regime of the spectrum of the operator. So whenever this is valid, we are going to look at our problem in that region. Okay? So in that region, we will show that these functions are that we considered are smooth. So for doing this, we recognize a couple of things. When you have a measure, a finite, let me take a probability measure. When you have a probability measure, then all the components of the measure in the Lebesgue decomposition can be captured by a transformation called the Stieltjes transform. So this quantity, if I take a measure, absolutely continuous measure, I can take any measure here, but if I take absolutely continuous measure with density G, then the Stieltjes transform, which is given by this transformation, and if I take the imaginary part, take the limit as epsilon goes to 0, that captures the density up to a factor of pi. This is a well-known theorem. So we are going to use this fact to compute the derivatives of this function g. So to show that this g has derivatives, it's enough because of this expression that I just simply look at the Stieltjes transform at the point I epsilon, take the derivatives and take the supremum over epsilon positive, and in an interval of my interest in the spectrum. So an estimate of this type will show me that I have so many derivatives for this density function. Okay, this is what I am going to use. So to take the Stieltjes transform, I simply look at the resolvents and take the averages. That gives me the Stieltjes transform of the measure. So here is a statement. So, if I take the measure ND, this is a distribution function. So, I look at the measure at the point E and look at the Still transform E minus Z, right. And what is this object? This object is nothing but H omega minus Z inverse, right. So, times P0 and trace, that is this object, that is not the object. This object is trace of P0 H omega minus Z inverse average, that is precisely this Still transform. So, to show that this object has a density which has so many derivatives, I have to compute the derivatives of this Still transform here as a function of Z, take the supremum over imaginary part of Z positive and take the supremum over real Z in some interval of interest. So, what I do is I approximate this operators by a sequence of finite rank operators, and then in that limit I try to show that all the quantities are bounded. So, once you have this limit, then the limiting quantity, which is what this object is, can be written in terms of a telescoping sum. If A n is a sequence that converges to A, then A can be written as sum of A n plus 1 minus A n over sum n going from 1 to infinity. So, the idea is write this limiting object in terms of these differences and somehow control the differences, show that they decay exponentially, so that this sum is controlled, and you can do this for derivatives. So, that is the central idea here. And for doing this, we just take the differences of boxes of size k plus 1 and k, take the resolvent difference, trace, average, take the derivatives. We know that these things are differentiable, because as I said, they are just convolutions with respect to on R n and R n plus 1. So, we can control the take the derivatives and control them, and so we have to show that the supremum of all these derivatives is finite. There is some horrendous calculation. So, the derivative of this difference, if you transfer it to the measure, it is going to be something like this, and that gives a factor of this type, some functions and average of this. Because we have a finite rank operator and we are taking the trace, it is enough to look at finitely many vectors for which you take the expectation value of this. For each of them you can show. Okay? So, we are going to look at something like this. Now, the problem is, how do we know that this difference of resolvents decays sufficiently in K to be able to control it? The expression that we have is only, if you remember my assumption was that the expectation of norm of P n H any lambda omega minus Z inverse P m. If I raise it to the power s smaller than 1, then this decays exponentially. Okay? So this is what is true. And if I look at these terms here, they are precisely of this form. I have a P0 here. This difference is like a Pk. So 0 to k, distance is k. And even on this side, P0 to k is distance is k. So I have terms like this. I have a term of this type. So how do I control this? So I have a term like P0 h lambda omega minus z inverse Pk h lambda something like this I have. Whereas I have to somehow raise it to a smaller power for me to get decay out of it. So that is obtained by a remarkable inequality, which is the following. If I take a self-adjoint operator A plus x times some positive bounded operator, then the resolvent multiplied by f to the power half, I can write it in this strange form. It is valid. 1 over x times identity minus 1 over x square, blah, blah, blah. So if I write it like this, then I can use, we prove a lemma of this type, which is the crucial lemma actually. So what does it say? Suppose A and B are self-adjoint operators, and f is a bounded positive operators, and z is a number with imaginary part positive. And suppose rho has compact support in 0 infinity and has alpha hollow continuous derivative for positive alpha. Its derivative is alpha hollow continuous. Then for some positive function rho tilde of compact support away from 0, we have this. I take A plus xf minus z inverse multiplied by f to the half minus b plus xf minus z inverse f to the half. A and B are self-adjoint operators. They can be bounded, unbounded, or whatever, doesn't matter. We just require f to be bounded and positive. Now take these operators. These are operators considered as decomposable operators on a direct integral Hilbert space with this measure. So these direct integral operators, I look at the direct integral. So that's an operator on a direct integral Hilbert space. I take that direct integral and look at its norm. I claim that the norm of that direct integral is bounded by the norm of this difference raised to the power s for s smaller than 1 and its integral with respect to some rho tilde that is related to rho. Now this is a remarkable identity, inequality. I don't think it's known in the literature, and it is this that makes it possible for us to use the exponential decay.
What's rho tilde related to rho? Complicated.
There is a relationship. It's not that's not a big deal. So here, as I said, A and B can be unbounded. Now this inequality written down like this may be difficult to understand, because what this seems to be telling you is that, which probably is not true, it seems to be telling us, suppose I take an integral of f of x rho of x dx and take the absolute value, then this is smaller than or equal to some constant times integral of absolute value of f of x to the power s rho of x dx. This is what it seems to be telling us. Rho tilde, yeah. This is what it seems to be telling us. When support of rho is away from in 0 infinity away from 0. This is counterintuitive. You never can get a smaller power than what you started with, right? Life would be great if you had such inequalities with absolute value. We could even take a positive function here. It seems to be saying this. But if you think about it a little bit, it is not saying that for anything. It's looking at a particular function. Okay, specific function like this, and for that function, it seems to be saying it. So the real, the heart of the issue here is the following. If I take a function of this type, 1 over x minus z, then z in the upper half plane, say, and I look at this integral for this particular function, 1 over x minus z rho x dx, and take the absolute value, then this function is the derivative of a logarithm. You can take the principal branch of the logarithm because z is in the upper half plane, that is well defined. So this function is well defined and its derivative is precisely this. So you take the derivative, and because we assume that rho has a derivative, I can do integration by parts and transfer the derivative here. And what I am left with is this logarithm is bounded if I take mod x minus z to the s times this absolute value. This is a bounded function when x minus z is close to 0. And because it is bounded, I can multiply by this and divide by that and get this inequality. Okay? So it is not true for it. The claim is not made that this inequality is true for all functions. For the specific function here, it seems to be true, and that helps because in the exponential decay statement, the assumption that we had powers of s average decays exponentially, provided they have a small power, s smaller than 1. So that is how we have to convert. So the idea is that in writing down the expression here, this function, this operator, we write as, after taking the trace and expectation, as a sum of finite dimensional operators. All of them are differentiable enough number of times based on rho, and because they are differentiable, if I can control this sum uniformly in some parameters, I will have that the limit also is smooth. And controlling these parameters requires this difference to be controlled, and that required the use of this inequality, for which we are using this lemma, that this difference of average with respect to one parameter is controlled by, is dominated by a power of s. And that's all that is the heart of the issue. And because this aspect was not recognized, 3 minutes, oh, okay. Because it was not recognized, the problem was open for a long time. So in any case, the way we prove it is that we recognize that the inverse, the resolvent can be written in terms of integral of a semigroup. We can rewrite this using that resolvent identity as the Fourier transform of this function multiplied by a contraction semigroup with parameter t, and then we get the estimates. Okay. Plus, we use the estimate for two contractions. You have this exponential bound, the fractional bound. So after doing all this, we finally show that objects like this are controlled in the average in some uniform way. So what this tells you is that these slides were prepared for experts, so that is why they look confusing. So the theorem is this. So let H omega be some bounded operator plus sum of omega n p n on a separable Hilbert space H. If you consider the spectrum E such that H omega minus E minus I epsilon inverse Pm P0 norm raised to the power S expectation is smaller than constant e to the minus some gamma times this is contained in the spectrum of H omega. I didn't tell you that for models such as this, the spectrum is a constant set almost everywhere. Therefore, you can have something inside here. So, if this set is non-empty, or suppose this contains an interval, J an interval, then whenever rho n's are omega n distributed like rho n are m times differentiable with rho n of m Holder continuous, then n e is in continuous functions on J. So that is the theorem. Okay, if the rho n's, which are the distributions of omega n, are m times differentiable plus a little Holder continuity, then this function is the distribution function of the spectral measure, averaged, trace. So let me recall that n of E is nothing but the expectation of trace of P0, the spectral measure of H omega 0 to minus infinity to E. That is this n. It is the distribution function of the measure. That's m times differentiable, which means that its density is m minus 1 times differentiable. So that is the theorem. This theorem also holds for the continuous model on L2 of RD. And L2 of RD, the even continuity of the density is a completely new theorem, even in any dimension. So, thank you.
Alone, then you have only continuous spectrum. So when you add the random, you get only discrete spectrum.
No, not only.
Because
No.
I'm trying to see the n
Okay.
discrete or continuous.
So the spectral questions are the spectral questions are a lot of unknown things there.
Yeah.
So what happens is that so if I take minus Laplacian plus sum of omega n u n and put a parameter lambda here, and you look at h omega of lambda. So Laplacian has the spectrum 0 to infinity. When lambda is large, when omega n's have absolutely continuous distribution, it is known that below this there is some spectrum AB. AB is B is smaller than or equal to 0, and the spectrum here is far away, is pure point. So from some point onwards is pure point, and this is the very first proof of this is by Peter Hislop and Jean-Michel Combe and other. These two have done it. That for large disorder you have pure point spectrum below some value. The exponential decay bounds were shown much more recently by Eisenman and others.
Is NE concerns the point spectrum or the continuous?
The theorem that I have
Yeah.
The NE concerns the entire spectrum.
Yeah.
But my theorem is only in this region. Okay. In fact, we don't even know what the spectrum is here. Once you take random operator, we don't know what kind of spectrum you have here. We know that the spectrum consists of the entire A to infinity. But we only know the spectrum below some closer to the bottom of the spectrum. We don't even know what is the spectral nature beyond. It's a completely open question.
I have a non-expert's question. What's the source of the non-standard resolvent identity? On which the remarkable
My student Anish Malik, he is the source.
So any other questions or comments? In that case, let us thank Krishna for a very nice talk.